Welcome, sleepy listener, to this quiet turning of the mind, where the boundaries of history grow a little porous, and the steady tick of the clock loosens its grip on us. If you've arrived tonight with a heart that wonders about what ifs, or a mind that likes to peer into the spaces between possibility and impossibility, you've found yourself in gentle company. This evening, we'll wander into a strange twilight of history, a place that never was, but could have been. We'll drift back, not to the early 20th century, when a young Albert Einstein startled the scientific world with his theories of space and time, but a full century before. And somewhere, impossibly, the equations of relativity are being inked onto yellowing paper long before the world is ready to receive them. And before we set sail into this alternate history, I'd love to know, where are you joining in from tonight? A bustling city, still lit with the glow of evening? A quiet countryside where the night air hums with insects? Or perhaps somewhere in between, in a small pocket of stillness carved out just for you? Imagine for a moment the jolt to our collective story if the laws that bend light and twist time were revealed before electric light bulbs, before railroads stitched continents together, before photography had even captured a single human face. Where does your mind go in such a world? To the practical wonders, technology centuries ahead of their time? Or to the unsettling thought that knowing too much too soon might bend history in ways we could never repair? So let's step carefully into this alternate century, where the ink of Einstein's pen stains a page in the wrong year, and time itself tilts ever so slightly. Take a slow breath, in and out, and let the steady beat of your own heart become a metronome for a history we are about to rewrite. The past is not fixed, not here. Shall we explore it together? Let's begin. Imagine, if you will, a world where the great tapestry of scientific understanding had been woven with different threads, where the delicate patterns of space and time revealed their secrets not in the clamor of the early 20th century, but in the quiet hush of the early 1800s. Picture for a moment Albert Einstein, born not in the age of steam engines and telegraphs, but in an era of candlelit libraries and horse-drawn carriages. His brilliant mind turning over the mysteries of the universe a full century before history intended. The year is 1805, and while Napoleon's armies march across Europe, a different kind of revolution is stirring in the mind of a young physicist gazing up at the stars from a small German village. The world around him still clings to the comforting certainties of Newtonian physics, time as an unwavering river, space as an immutable stage, and the universe as a grand, predictable clockwork. But in this alternate history, Einstein is already beginning to see beyond these illusions, sensing the hidden rhythms of a cosmos far more fluid and mysterious than anyone had dared to imagine. The story begins not with fanfare or sudden revelation, but with a quiet thought, one that might have come to him on a still evening as he watched the flicker of a candle's flame or the steady glow of a distant star. What if light, that most ethereal and ancient of phenomena, did not behave as the textbooks claimed? What if its speed was not merely another measurement to be cataloged, but a fundamental constant of the universe, unchanging and absolute, no matter how fast an observer moved toward or away from its source? This simple yet radical idea would have been the first loose thread in the tightly woven fabric of classical physics, a single tug that threatened to unravel centuries of unshakable assumptions. In this world, the scientific establishment of the early 19th century would have been utterly unprepared for such a revelation. The notion that time itself could stretch and compress like taffy, that two events occurring simultaneously for one observer might unfold at different moments for another, would have seemed like the stuff of dreams or madness. The very foundations of reality, solid and dependable to the minds of Newton's heirs, would have trembled at the suggestion that space and time were not separate and absolute, but intimately entwined, bending and warping in response to matter and motion. And yet, this was the essence of Einstein's genius, his ability to question the unquestionable, to peer beyond the visible and grasp the hidden architecture of the cosmos. His thought experiments, those elegant, almost meditative exercises in imagination, would have been the same, whether in 1805 or 1905. A man riding alongside a beam of light, watching it ripple outward like a wave frozen in time. A passenger on a moving train, observing a clock tower as it ticked at a different pace than the watch in his pocket. These were not flights of fancy, but careful probes into the nature of reality, designed to expose the contradictions lurking beneath the surface of classical physics. But in this earlier era, the tools to test or even fully comprehend these ideas would have been scarce. Without precise atomic clocks, without the ability to measure the subtle distortions of starlight bending around the sun, relativity might have remained a beautiful but untested theory for decades, a secret passed between mathematicians and philosophers in hushed tones. Yet, the mere existence of these ideas would have cast a long shadow over the scientific landscape. Like a stone dropped into a still pond, the ripples of Einstein's early insights would have spread slowly but inexorably, altering the course of inquiry in ways both subtle and profound. The 19th century, so often remembered for its industrial might and mechanical ingenuity, might also have become an age of quiet cosmological revolution, a time when humanity first began to glimpse the fluid, dynamic nature of the universe. The poets and artists of the Romantic era, already enchanted by the sublime and the infinite, might have found in relativity a new language for their awe, a scientific echo of their own intuitions about the interconnectedness of all things. And so, as we settle into this thought experiment, let us imagine the world as it might have been. A world where the stars yielded their secrets a little sooner, where the boundaries between space and time were revealed not in the cacophony of the modern age, but in the stillness of an earlier, more contemplative time. The journey ahead is long and winding, but each step will bring us deeper into the heart of this alternate history, where the equations of relativity were penned not in ink, but in the soft light of oil lamps, and where the universe, in all its mystery, whispered its truths to a world only half prepared to hear them. As the early 19th century unfolded in this alternate timeline, Einstein's ideas would have encountered a world still deeply rooted in Newtonian certainties. The scientific community of the 1800s, though brilliant in its own right, lacked both the mathematical language and the experimental tools to fully grasp the implications of relativity. Picture the learned societies of Europe, gentlemen scientists in powdered wigs and waistcoats gathering in candlelit halls to debate the nature of gravity, still firmly convinced of its instantaneous action across empty space. Into this world steps a young Einstein, armed only with his thoughts and the quiet conviction that the universe operates by different rules than those laid down by the great Newton. The first murmurs of discontent would have been subtle. Perhaps it began with a paper submitted to the Annalen der Physik in 1807, written in elegant German script, suggesting that the speed of light might be constant regardless of the observer's motion. To the physicists of the day, this would have seemed not just counterintuitive, but nearly heretical. After all, if a man ran toward a beam of light, shouldn't he perceive it moving faster? The very notion violated their understanding of relative motion, so beautifully explained by Galileo centuries before. The scientific establishment might have dismissed these ideas as the musings of an overactive imagination, much as they initially dismissed the concept of meteorites falling from space. Yet Einstein would have persisted, his mind returning again and again to the paradoxes that classical physics couldn't resolve. He might have imagined a clock mechanism so precise it could measure the infinitesimal slowing of time for a moving observer, though no such clock existed in his era. He would have pondered the strange behavior of Mercury's orbit, its perihelion precession already hinting at flaws in Newton's gravity, though it would be decades before astronomers accumulated enough data to notice the discrepancy. Without the benefit of Maxwell's equations, still half a century away in this timeline, Einstein's path to special relativity would have been more arduous, built on pure thought experiments rather than the elegant unification of electricity and magnetism. The philosophical implications alone would have shaken the foundations of Enlightenment thinking. In an age when Kant was still writing about the categories of human understanding, the suggestion that time and space were not absolute frameworks, but malleable constructs would have sent shockwaves through intellectual circles. Artists and poets of the Romantic movement, already fascinated by subjectivity and perception, might have seized upon these ideas, weaving them into their exploration of human consciousness. The very notion that two observers could disagree about the simultaneity of events, depending on their motion, would have resonated deeply in a Europe beginning to question absolute truths of all kinds. Meanwhile, the practical limitations of the era would have created fascinating challenges. Without photography, let alone the sophisticated instruments of 20th century physics, how could one prove these radical ideas? Einstein might have suggested looking for the aberration of starlight at different times of year, or proposed thought experiments involving synchronized pocket watches on moving trains, concepts just barely within the technological grasp of the early Industrial Revolution. The scientific method itself would have been tested as researchers struggled to validate through reason what they couldn't yet confirm through experiment. In this world, mathematics would have become the primary language of the new physics. The Lorentz transformations, which describe how measurements of space and time change between moving frames of reference, might have been derived purely theoretically decades before Hendrik Lorentz's birth. The elegant symmetry of these equations would have appealed to mathematicians like Gauss and Cauchy, who might have recognized in them a beautiful new geometry of space-time waiting to be uncovered. The tensor calculus that Einstein later used to formulate general relativity might have been developed earlier as mathematicians raced to provide tools for these revolutionary ideas. The social reception of these theories would have followed a fascinating path. At first, confined to academic circles, the concepts might have trickled into popular culture through salons and coffee houses, where intellectuals debated the nature of reality over cups of steaming brew. Newspapers might have carried sensationalized accounts of Einstein's crazy clock paradox, while more thoughtful periodicals pondered the philosophical implications. The Church, already grappling with geological evidence of an ancient Earth, would have faced new challenges to its conception of absolute time, potentially accelerating the dialogue between science and religion that characterized the later 19th century. As the decades passed, the accumulating weight of indirect evidence might have slowly convinced the scientific community. Astronomers noticing anomalies in the orbit of Mercury, physicists observing subtle effects in the behavior of light, mathematicians delighting in the elegant consistency of the new theories, all would have contributed to a gradual acceptance of relativity, much as Darwin's ideas gained traction over time. By the 1830s, a generation of young scientists raised on these concepts might have begun developing the experimental techniques to test them properly, setting the stage for a technological revolution built on this new understanding of the universe. The most profound change, however, would have been in humanity's conception of its place in the cosmos. In a single stroke, Einstein's early theory would have dethroned Earth from its position at the center of an absolute space and time, revealing instead a universe where all perspectives were equally valid, where the very fabric of reality depended on one state of motion. This democratization of physics would have mirrored and perhaps accelerated the political revolutions sweeping across Europe and America, creating a cultural moment where the questioning of all absolute authorities, scientific, political, and religious, became the spirit of the age. As the 19th century progressed in this alternate timeline, Einstein's radical ideas would have begun permeating far beyond the halls of academia, subtly reshaping humanity's understanding of its place in the cosmos. Imagine the year 1820. Gas lamps flickering in cobblestone streets, steam engines chugging along newly laid tracks, but yet, beneath these familiar sights, an intellectual revolution quietly unfolding. The notion that time itself could flow at different rates for different observers would have challenged the very foundations of how people conceptualized reality. The scientific community would have divided into passionate factions. Traditionalists, clinging to Newton's absolute space and time, might have dismissed relativity as mathematical sophistry. Meanwhile, forward-thinking physicists would have recognized they stood at the precipice of a new era. Without experimental confirmation, the debate would have raged in philosophical terms, with thought experiments replacing laboratory evidence. Picture learned societies hosting heated debates where gentlemen scientists argued whether two events truly could be simultaneous for one observer, but not another, their voices rising in candlelit chambers filled with pipe smoke and the rustle of wool coats. Mathematics would have advanced at an astonishing pace to keep up with these theoretical developments. The need to describe curved spacetime might have accelerated the creation of non-Euclidean geometries decades before Riemann. Gauss, hearing of Einstein's ideas, might have seen in them the perfect application for his work on curved surfaces. The cross-pollination between pure mathematics and physics would have blossomed earlier, creating a golden age of theoretical exploration where abstract concepts found immediate application in describing the physical world. The technological limitations of the era would have created fascinating paradoxes. While the theory predicted that fast-moving clocks would run slow, no timekeeping device of the 1820s could possibly detect such minute differences. This disconnect between theory and verification might have led to beautiful thought experiments, becoming the primary method of exploration. Scientists would have imagined increasingly elaborate scenarios involving hypothetical perfect clocks and light beams, their minds straining to comprehend a universe far stranger than their instruments could reveal. Philosophy would have undergone its own revolution. Kant's transcendental idealism, with its separation of phenomena and noumena, would have found startling confirmation in the realization that space and time were not absolute, but observer-dependent. Romantic poets like Wordsworth and Coleridge, already fascinated by the relationship between perception and reality, might have incorporated relativistic concepts into their works. The line between science and philosophy would have blurred as thinkers grappled with the implications of a universe where measurement altered the very fabric of existence. Astronomy would have been the first field to find potential evidence for these radical ideas. Careful observations of binary stars might have revealed anomalies in their apparent motion that classical physics couldn't explain. The precession of Mercury's orbit, which in our timeline became key evidence for general relativity, would have been noticed earlier and taken more seriously as a challenge to Newtonian gravity. Astronomers would have begun looking at the heavens with new eyes, searching for other phenomena that might confirm or contradict Einstein's theories. The arts would have reflected this changing worldview. Painters of the Romantic era, already breaking from classical traditions, might have developed new techniques to represent the relativity of perception. Imagine Turner's seascapes with subtly distorted perspectives hinting at curved space-time, or Beethoven composing symphonies with tempo variations that mirrored time dilation. Literature would have explored the human implications of these ideas, with novels pondering characters separated by both distance and the flow of time itself. Religious institutions would have faced profound questions. The notion that time was malleable rather than absolute would have challenged traditional interpretations of creation and eternity. Liberal theologians might have embraced these ideas as revealing God's universe to be even more marvelous than previously imagined, while conservative elements might have seen them as threatening the orderly universe described in Scripture. This tension could have accelerated the dialogue between science and religion that, in our timeline, took another century to develop. Education would have transformed as these concepts filtered into curricula. The classical physics that had formed the foundation of scientific training for generations would have been supplemented and sometimes supplanted by these new ideas. Bright young minds across Europe would have pored over papers describing the relativity of simultaneity, their worldviews expanding even as they struggled to reconcile these concepts with everyday experience. The very language of science would have evolved earlier to describe these phenomena, with terms like space-time and reference frame entering common usage decades before they did in our timeline. The social implications would have been equally profound. In an age of revolutions and challenges to traditional authority, the democratization inherent in relativity, the idea that no observer's perspective was privileged over another, would have resonated with political reformers. The connection between scientific and social revolution would have become explicit earlier, with thinkers drawing parallels between the overthrow of absolute space and time and the overthrow of absolute monarchy. The egalitarian implications of a universe where all inertial frames were equally valid might have become a metaphor for emerging democratic ideals. As the 1830s dawned, the stage would have been set for the next great leap. The foundations of special relativity, though still awaiting experimental confirmation, would have become increasingly accepted among forward-thinking scientists. The most brilliant minds of the generation would have turned their attention to the next logical question. If space and time were relative, what about gravity? In quiet studies across Europe, on slates covered with chalk dust, and in notebooks filled with precise script, the first inklings of general relativity would have begun to take shape, promising to reveal an even deeper truth about the warped geometry of the cosmos. As the 1830s unfolded in this alternate timeline, the scientific world stood poised on the brink of an even greater revelation. The acceptance of special relativity had already stretched minds to their limits, but now Einstein turned his attention to the remaining piece of the puzzle: gravity. Picture him in his modest study, quill in hand, staring at an apple resting on his desk, much like Newton centuries before. But where Newton saw a force, Einstein saw a curvature, a bending of the very stage upon which the universe performed its endless dance. The concept that gravity was not a force, but the warping of space-time itself, would have seemed even more radical than his earlier work, challenging not just physics, but humanity's most basic intuitions about how the world worked. The mathematics required to describe curved space-time would have pushed the boundaries of contemporary knowledge. Gauss, then in his later years, might have corresponded with the young Einstein about the geometry of curved surfaces, recognizing in the physicist's questions the practical application of his abstract mathematical theories. Riemann, still a child, would grow up in a world already primed for his groundbreaking work on manifolds and differential geometry. The tensor calculus that took Einstein a decade to master in our timeline might have been developed cooperatively by mathematicians racing to provide tools for these revolutionary physical concepts. Astronomers would have become crucial allies in this intellectual revolution. Without the technology to create strong gravitational fields for experimentation, scientists would have turned their gaze upward, to the natural laboratories provided by the cosmos. The anomalous orbit of Mercury, which in our timeline provided key evidence for general relativity, would have been scrutinized even more intensely. Observations of starlight bending during solar eclipses, though still decades away from being measurable with 1830s technology, would have been predicted theoretically, creating a tantalizing goal for future generations of astronomers. The philosophical implications would have been staggering. The idea that space itself could curve, that the path of a falling apple and the orbit of the moon were both following the straightest possible path through warped geometry, would have forced a complete reimagining of basic concepts like straight and flat. Philosophers would have wrestled with the question of whether this curvature was real or merely a mathematical convenience, a debate that continues to some extent even today. The very language of physics would have had to evolve to describe these concepts, with words like geodesic and metric tensor entering the lexicon much earlier. The technological limitations of the era would have created both frustration and opportunity. Without precise atomic clocks or space-based experiments, many predictions of general relativity would have remained untested. This might have led to an unusual situation where an advanced theoretical framework outpaced experimental verification by nearly a century. Yet this delay could have fostered a golden age of theoretical physics, where mathematical elegance and internal consistency became the primary measures of a theory's validity, much as they had been for the ancient Greeks. The arts would have responded to these ideas in fascinating ways. Romantic poets might have written of warped space and time's malleable fabric, using these scientific concepts as metaphors for human emotion and experience. Landscape painters, already experimenting with perspective, might have created subtle visual distortions in their work to represent the curvature of space. Composers could have experimented with musical motifs that bent and twisted back on themselves, creating auditory representations of curved spacetime. The line between scientific illustration and artistic expression would have blurred in exciting new ways. Religious thought would have faced another profound challenge. The notion that gravity resulted from the warping of an invisible spacetime fabric would have raised deep questions about the nature of creation. Some theologians might have embraced this as evidence of God as the ultimate geometer, while others might have seen it as reducing divine action to mere geometry. The debate would have mirrored in many ways the earlier controversies over Copernican astronomy, but with even more abstract and far-reaching implications. Education systems across Europe would have struggled to adapt. The classical curriculum, based on Newtonian physics and Euclidean geometry, would have seemed increasingly outdated. Progressive educators might have developed new teaching methods to help students visualize four-dimensional spacetime, perhaps creating physical models or interactive demonstrations. The very way mathematics was taught would have shifted earlier toward more abstract and conceptual approaches, preparing young minds for the new physics. The social impact would have been subtle but significant. In an age of growing industrialization, the realization that even space and time were not rigid and absolute might have influenced critiques of the rigid social hierarchies of the time. The interconnectedness revealed by relativity, the way observers in different states of motion could validly perceive different realities, might have fostered earlier appreciation for diverse perspectives in other realms of human thought. As the 1840s approached, the scientific community would have found itself in an unusual position. Armed with a sophisticated theoretical framework that promised to explain everything from falling apples to the motion of planets, yet lacking the technology to confirm its most startling predictions. This tension between theory and experiment would have defined the coming decades, as scientists and inventors raced to build the instruments that could test Einstein's radical vision of a curved, dynamic universe. The stage was set for a technological revolution that would, in time, catch up to the revolution in thought that had already occurred. As the 19th century reached its midpoint in this alternate timeline, the ripples of Einstein's theories began manifesting in unexpected ways across science and society. Picture the year 1850, steamships crossing oceans, telegraph wires stitching continents together, and yet beneath these tangible advances, an invisible revolution in human understanding was quietly unfolding. The concepts of space-time curvature and relative simultaneity, once confined to academic circles, had begun permeating the broader intellectual landscape, subtly altering how people conceptualized their place in the universe. The scientific community found itself navigating uncharted waters. Without experimental confirmation of relativity's predictions, the field had bifurcated into two parallel streams. Traditional Newtonian physics continued to dominate practical engineering and mechanical applications. After all, steam engines and bridges needed no knowledge of time dilation to function properly. Meanwhile, theoretical physics had leaped ahead to contemplate phenomena far beyond what contemporary technology could verify. This created a peculiar situation where the most advanced physics seemed almost like a form of mathematical philosophy, its truths derived through pure reason rather than empirical observation. Astronomy became the battleground where these competing worldviews clashed. The precise tracking of Mercury's orbit continued to show discrepancies with Newtonian predictions, providing tantalizing but inconclusive support for Einstein's geometric theory of gravity. Telescopes of the era, while improving rapidly, still lacked the resolution to detect the subtle bending of starlight near the sun, an observation that would have provided the smoking gun evidence for general relativity. Astronomers began planning ambitious eclipse expeditions decades earlier than in our timeline, recognizing these celestial events as rare opportunities to test the revolutionary theory. The mathematical tools needed to describe curved spacetime evolved at an astonishing pace. Where Einstein in our timeline had to master Riemannian geometry on his own, in this alternate 1850s, the work was being carried forward by an entire generation of mathematicians inspired by the applications of their abstract theories. Differential geometry became a vibrant field years ahead of schedule, with papers flowing between physics and mathematics departments in an unprecedented cross-pollination of ideas. The tensor calculus that would later underpin general relativity was being developed cooperatively rather than by a single isolated genius. Industrial applications of these abstract concepts remained limited, but visionary inventors began speculating about potential technologies. Some dreamed of precision timekeeping devices that could detect relativistic effects, unknowingly anticipating the atomic clocks of the 20th century. Others pondered whether the energy-mass equivalence hinted at in Einstein's papers might have practical applications, though none could yet imagine nuclear power. The most forward-thinking engineers began incorporating relativistic considerations into their designs for electrical systems, recognizing that Maxwell's emerging equations of electromagnetism would need to be reconciled with the new physics. The philosophical consequences deepened as these ideas spread. The radical subjectivity implied by relativity, where different observers could legitimately disagree about fundamental measurements like length and duration, resonated powerfully in an era increasingly preoccupied with individual perspective. Romanticism's focus on subjective experience found scientific validation in the realization that even time itself flowed differently for different observers. Philosophers began speaking of relativism decades before the term took on its modern cultural meanings, using it first in strict reference to physics before extending it to other domains of human thought. Educational systems struggled to adapt to these paradigm shifts. Progressive universities began introducing courses on the new physics, while conservative institutions clung stubbornly to classical mechanics. Textbook authors faced the peculiar challenge of explaining concepts that lacked experimental verification, developing elaborate thought experiments and analogies to convey ideas that defied everyday experience. The brightest students found themselves torn between the practical certainty of Newton and the thrilling possibilities of Einstein, with some choosing to devote their careers to building the experimental infrastructure needed to test these radical theories. The arts continued to absorb and reinterpret these scientific breakthroughs. Poets wrote of time's river bending back upon itself, while novelists experimented with narrative structures that played with relative simultaneity, having characters experience the same events in different orders depending on their perspective. Visual artists, freed from strict representationalism by the camera's invention, began creating works that hinted at spatial distortion and multiple viewpoints. Even architecture showed subtle influences, with some designers experimenting with curved spaces that evoked relativistic geometry. Religious thinkers developed increasingly sophisticated responses to the new physics. Liberal theologians reinterpreted sacred texts through the lens of relative time and curved space, finding new ways to reconcile science and spirituality. More conservative factions doubled down on literal interpretations, setting the stage for conflicts that would play out over coming decades. The concept of a beginning to the universe took on new urgency in theological debates as relativistic cosmology suggested possibilities both for and against traditional creation narratives. As the 1850s progressed, the first generation of scientists raised entirely on relativistic thinking began coming of age. These young minds, unburdened by Newtonian preconceptions, started asking questions their teachers couldn't answer and imagining experiments their technology couldn't yet perform. The stage was being set for an explosion of theoretical and technological innovation that would, in time, transform these abstract mathematical concepts into concrete realities. The relativistic revolution, born from pure thought decades before its time, waited only for material science to catch up with human imagination. As our imagined timeline enters the latter half of the 19th century, the seeds planted by Einstein's early work begin bearing unexpected fruit across multiple disciplines. The 1860s dawn with a scientific community that has grown more comfortable living with two parallel physical frameworks: the reliable, practical Newtonian worldview for everyday phenomena, and the more radical Einsteinian understanding for fundamental questions about the universe's fabric. This duality creates a fascinating intellectual tension that drives innovation in both theory and experimentation. The development of more precise astronomical instruments finally begins providing concrete evidence for relativistic predictions. Astronomers tracking Mercury's orbit now have telescopes with precision micrometers and photographic plates, allowing them to confirm with certainty that its perihelion advance exceeds Newtonian predictions by exactly the amount Einstein's equations suggest. This verification sends shockwaves through scientific circles, converting many remaining skeptics. Meanwhile, expeditions to observe the 1868 solar eclipse, though still unable to definitively measure light bending, return with data showing subtle anomalies in stellar positions that align suspiciously well with relativistic calculations. Mathematics undergoes another revolution as the demands of relativity theory spur development of new analytical tools. The work of Bernard Riemann, who in this timeline focuses even more intensely on differential geometry at Einstein's encouragement, provides the perfect language for describing curved space-time. Sophisticated tensor calculus notation spreads through European universities, initially meeting resistance from traditionalists who find its complexity unnecessary, until a brilliant young mathematician named Gregorio Ricci-Curbastro begins developing the absolute differential calculus that will later prove essential for general relativity's full formulation. The philosophical landscape continues evolving in fascinating ways. The German idealists, particularly followers of Hegel, seize upon relativity as scientific validation of their dialectical approach to truth. The concept that observers in different frames of reference can legitimately perceive different realities resonates powerfully with philosophical trends emphasizing perspective and subjectivity. This creates unexpected bridges between science and philosophy, with university courses beginning to examine physics and metaphysics as complementary rather than opposing disciplines. Industrial applications remain limited, but begin emerging in surprising areas. The growing telegraph network, with its need for precise time synchronization across continents, provides the first practical arena where relativistic time dilation must be considered, albeit at an extremely subtle level. Engineers designing transatlantic cables begin consulting physics papers about reference frames and simultaneity, creating the first generation of applied relativists. Meanwhile, the development of more accurate mechanical clocks, some achieving precision within hundredths of a second per day, allows physicists to begin designing experiments to test time dilation, though the effects remain too small to measure with 1860s technology. The social impact of relativity deepens as analogies spread through popular culture. Political reformers draw parallels between the relativity of physical measurements and the relativity of social truths, using Einstein's theories to argue against absolutism in governance. The women's rights movement finds metaphorical power in the idea that different observers can experience fundamentally different realities while all being equally valid. Even economic theorists begin exploring how relativistic concepts might apply to value and exchange, though these analogies often stretch the science beyond reasonable limits. Educational systems reach a turning point as relativity becomes institutionalized. The first dedicated textbooks on modern physics appear in German and French, attempting to present Einstein's ideas in systematic fashion to university students. Traditional geometry curricula expand to include non-Euclidean approaches, with progressive schools using models of curved surfaces to help students visualize space-time distortion. A new generation enters university already familiar with basic relativistic concepts, allowing professors to focus on more advanced implications rather than battling Newtonian preconceptions. The arts undergo another wave of relativistic inspiration. Composers like Liszt and Wagner experiment with musical time dilation, stretching and compressing thematic material in ways that play with a listener's perception of duration. Painters of the emerging Impressionist movement find kinship with relativity's challenge to absolute perception, creating works that emphasize how light and form change with perspective. Literature sees the birth of early science fiction, with Jules Verne's later works including speculative elements about time distortion at high velocities, though the technology to achieve such speeds remain firmly in the realm of fantasy. Religious institutions gradually develop more nuanced responses to the new physics. The Vatican's scientific advisors, after decades of cautious study, issue a statement acknowledging that relativity theory does not inherently contradict Catholic doctrine about time and eternity. Protestant denominations divide along familiar lines, with liberal theologians embracing the new cosmology as revealing God's grandeur through science, while fundamentalist groups condemn it as another dangerous departure from biblical truth. Eastern spiritual traditions, particularly Hinduism and Buddhism, find striking parallels between relativistic concepts and their ancient teachings about the illusion of separateness and the fluidity of time. By the 1870s, the focus of theoretical physics begins shifting toward unification. Einstein, now entering his later years, turns his attention to merging electromagnetism with his geometric theory of gravity, the first steps toward what in our timeline would become the quest for a unified field theory. Meanwhile, a young James Clerk Maxwell finds himself working in a scientific landscape already transformed by relativity, and his equations of electromagnetism are formulated from the start with relativistic considerations in mind, creating an even more elegant mathematical synthesis than in our history. The stage is now set for the final act of this scientific revolution. As the 19th century enters its last decades, all the pieces are in place for relativity to make the transition from theoretical framework to experimental reality and practical application. The world stands on the brink of a technological revolution that will at last provide tools to test and implement these ideas that have lived so long in the realm of pure thought. The marriage of abstract theory and concrete engineering, delayed by nearly a century in this timeline, is finally about to be consummated. As the final decades of the 19th century unfolded in this alternate timeline, Einstein's revolutionary ideas, born nearly a century ahead of their time, finally began to transition from abstract theoretical constructs to measurable physical reality. The period between 1880 and 1900 witnessed an extraordinary convergence of theoretical insight and technological capability that allowed humanity, for the first time, to truly test and apply the principles of relativity in concrete ways. The world stood at the threshold of a new era, where the subtle warping of space-time would move from mathematical equations to observable phenomena, forever altering humanity's relationship with the cosmos. The long-awaited experimental verification of general relativity arrived through several groundbreaking astronomical observations during the 1880s. The development of precision spectroscopes and improved photographic plates enabled astronomers to finally detect the gravitational redshift of light, a key prediction of Einstein's theory that light climbing out of a gravitational well should lose energy and shift toward the red end of the spectrum. At the Harvard College Observatory, meticulous measurements of sunlight revealed the faint but unmistakable signature of this effect, providing the first direct evidence that gravity affected light as relativity predicted. Meanwhile, the total solar eclipse of 1882 saw teams of astronomers dispatched to remote locations across the globe, armed with the latest photographic equipment capable of capturing star positions near the sun's obscured disk with unprecedented accuracy. When the plates were developed and analyzed months later, they showed the telltale bending of starlight around the sun's massive gravitational field. Not the Newtonian value of 0.87 arcseconds, but the full 1.75 arcseconds predicted by general relativity. The scientific world erupted in excitement as these confirmations arrived, with newspapers across Europe and America announcing Einstein's triumph, nearly 80 years after he first proposed his radical theories. The technological implications of relativity began manifesting in unexpected ways during this period. The growing global network of railroads and telegraphs created an acute need for precise time synchronization across continents, forcing engineers to grapple with relativistic effects that were infinitesimal but conceptually revolutionary. The International Meridian Conference of 1884, while primarily concerned with establishing standard time zones, found itself embroiled in unexpected debates about the relativity of simultaneity and how to account for slight time differences between moving reference frames. Although the practical impact remained negligible for most applications, the mere acknowledgement of these effects in official timekeeping standards represented a profound philosophical shift, humanity's first institutional recognition that time was not absolute, but relative. Meanwhile, the development of electrical power systems provided another arena where relativistic concepts proved unexpectedly relevant. As alternating current systems spread across cities and continents, engineers designing long-distance power transmission began encountering phase shift effects that bore curious mathematical similarities to relativistic transformations between reference frames. While the underlying physics was different, this parallel helped create a generation of technically minded professionals comfortable thinking in terms of relative measurements and coordinate transformations. The emerging field of electrical engineering thus became an unlikely vector for spreading relativistic thinking beyond academic physics departments. The mathematical tools needed to fully exploit relativity theory advanced dramatically during these decades. The tensor calculus developed by Gregorio Ricci Carbistro and Tullio Livicivita provided exactly the rigorous framework needed to express Einstein's field equations with precision. What had begun as an obscure branch of differential geometry now found itself at the center of cutting-edge physics, with mathematics departments across Europe scrambling to offer courses in these new methods. The beautiful interplay between abstract mathematics and physical theory reached new heights as physicists and mathematicians engaged in an intense cross-disciplinary dialogue that enriched both fields. This collaboration laid the groundwork for the even more sophisticated mathematical physics that would emerge in the early 20th century. Industrial applications of relativity remained limited, but began occurring in fascinating niches. Precision instrument makers, catering to the growing scientific demand for accurate measurements, developed the first generation of relativistic chronometers, mechanical clocks designed to maintain synchronization while in motion, accounting theoretically, if not yet practically, for time dilation effects. While these devices couldn't actually measure relativistic time differences with 1880s technology, their very existence testified to how deeply Einstein's ideas had penetrated engineering consciousness. More practically, the emerging science of ballistics began incorporating relativistic corrections into long-range artillery calculations, though the effects remained negligible at terrestrial velocities. The philosophical impact of relativity deepened as experimental confirmation removed lingering doubts about its physical validity. The concept that space and time formed a malleable fabric rather than a fixed stage fundamentally altered humanity's cosmological perspective. Philosophers grappled with the implications of a universe where the distinction between here and now depended on one's state of motion, where gravity was not a force but the curvature of space-time itself. These ideas resonated powerfully with the growing modernist movement in arts and literature, providing a scientific foundation for the era's questioning of absolute truths and fixed perspectives. The French philosopher Henri Bergson's work on the subjective experience of time took on new dimensions when considered alongside relativity's rigorous framework, creating rich dialogues between physics and phenomenology. Educational systems underwent their most dramatic transformation yet, as relativity became standard curriculum. By the 1890s, leading universities in Germany, France, and Britain offered dedicated courses on modern physics that presented Einstein's theories as established fact rather than speculative hypothesis. Textbook publishers produced lavishly illustrated volumes using the latest printing technology to depict space-time curvature and light cone diagrams, helping students visualize these abstract concepts. Even secondary schools began introducing simplified versions of relativistic principles, with progressive educators developing hands-on demonstrations using stretched fabrics and rolling marbles to simulate gravitational warping. A student graduating from a European gymnasium in 1895 would have possessed a conceptual understanding of relativity that in our timeline didn't become widespread until the 1950s. The arts continued to absorb and reinterpret relativistic concepts in increasingly sophisticated ways. The symbolist movement in literature, with its emphasis on subjective experience and the fluidity of perception, found scientific validation in relativity's challenge to absolute space and time. Poets like Stefan Mallarmé composed works that played with temporal simultaneity and perspective shifts, while composers such as Claude Debussy experimented with musical structures that evoked space-time's four-dimensional continuum. Visual artists, particularly those associated with the emerging post-impressionist movement, created works that deliberately distorted perspective and played with multiple viewpoints, translating relativistic ideas into visual form years before Cubism would attempt similar experiments in our timeline. Religious institutions, after decades of cautious observation, began developing more nuanced theological responses to the new physics. The Vatican's Pontifical Academy of Sciences issued a series of statements clarifying that relativity theory, while challenging to traditional conceptions of time and space, did not inherently contradict Catholic doctrine about creation or eternity. Protestant denominations varied in their responses, with liberal theologians enthusiastically embracing the new cosmology as evidence of God's infinitely creative mind, while conservative factions condemned it as another dangerous departure from biblical literalism. Eastern spiritual traditions, particularly Hinduism and Buddhism, found striking parallels between relativistic concepts and their ancient teachings about the illusion of separateness and the fluidity of time, leading to unprecedented dialogues between Eastern mystics and Western physicists. The social and political ramifications of relativity became increasingly apparent as the century drew to a close. The theory's emphasis on the equality of all inertial reference frames provided powerful metaphorical ammunition for social reformers advocating equality across class, gender, and racial lines. Feminist thinkers drew parallels between the relativity of physical measurements and the cultural construction of gender roles, while anti-colonial activists used relativistic arguments to challenge Eurocentric views of history and progress. Even as these social movements appropriated scientific concepts sometimes beyond their intended meaning, the widespread cultural absorption of relativistic thinking created an intellectual climate more receptive to challenging absolute hierarchies of all kinds. As the 19th century gave way to the 20th in this alternate timeline, the stage was set for relativity's principles to transform not just physics, but the entire technological landscape. The groundwork had been laid for applications ranging from precision navigation to energy generation, applications that in our timeline took another half-century to emerge. Most importantly, several generations had now grown up with relativity as established science rather than revolutionary novelty, creating a population conceptually prepared for the even more startling revelations quantum physics would soon bring. The world stood poised on the brink of a new century that would see Einstein's century-early insights bear fruit in ways even he could scarcely have imagined. As the new century unfolded in this alternate timeline, the world found itself in the extraordinary position of entering the 20th century with relativity already a mature scientific framework. The period from 1900s to 1920s witnessed an explosion of theoretical and technological developments, building upon Einstein's century-early insights, creating a scientific landscape dramatically different from our own history. The foundations laid in previous decades now supported structures of understanding and innovation that would permanently alter humanity's relationship with matter, energy, and space-time itself. Theoretical physics entered a golden age as researchers explored the consequences of relativity with mathematical tools and conceptual frameworks that had developed alongside the theory. Without the need for the paradigm shifts that consumed physics in our early 20th century, scientists could focus immediately on pushing relativity to its limits and exploring its connections to other phenomena. The first attempts at unified field theories emerged as early as 1905, with several European physicists working to reconcile electromagnetism with Einstein's geometric description of gravity. These efforts, while ultimately unsuccessful, accelerated the development of sophisticated mathematical techniques that would later prove crucial for quantum theory. The most dramatic breakthrough came with the experimental verification of mass-energy equivalence. In our timeline, expressed as E is equals to mc squared, this revolutionary insight had been part of the theoretical framework since Einstein's early work, but only now did technology permit its direct confirmation. The development of precise calorimeters and sensitive radiation detectors allowed physicists to measure the tiny mass changes accompanying nuclear reactions. At the Cavendish Laboratory in Cambridge, careful experiments with radioactive elements demonstrated incontrovertibly that the energy released corresponded exactly to the minute but measurable loss of mass predicted by relativity. This confirmation, published in 1908, opened eyes to the staggering energy potential locked within atomic nuclei, though harnessing this energy remained far beyond current capabilities. Astronomy continued to be transformed by relativistic insights. The completion of major observatories, like Mount Wilson's 60-inch reflector telescope, provided data that consistently supported general relativity's predictions. Measurements of starlight bending during solar eclipses became routine, with each new observation matching Einstein's equations with uncanny precision. Astronomers began applying relativistic corrections to all their calculations, from planetary orbits to binary star systems, achieving levels of accuracy previously unimaginable. The growing acceptance that light itself had weight and followed curved paths through warped space-time fundamentally changed how scientists interpreted their observations of distant cosmic phenomena. Technological applications of relativity began moving from theory to practice in this period. The most immediate impact came in timekeeping and navigation. As the world's transportation networks grew more sophisticated, the need for precise synchronization between moving reference frames became critical. Shipboard chronometers now incorporated small but deliberate adjustments based on relativity, accounting for both velocity time dilation, special relativity, and gravitational time dilation, general relativity. While the effects remained minuscule for terrestrial applications, amounting to nanoseconds over transatlantic voyages, the principle of accounting for them became standard practice, establishing a conceptual framework that would prove crucial for later technologies. The emerging field of aviation provided another unexpected testing ground for relativistic concepts. While aircraft of the era couldn't approach speeds where relativistic effects became significant, engineers designing instrumentation began considering these factors in their calculations. The first aerial navigation systems incorporated relativistic corrections in their theoretical foundations, ensuring they would remain accurate as aircraft speeds increased in future decades. This forward-thinking approach meant that when jet aircraft eventually arrived, their navigation systems were already designed with relativity in mind, avoiding the problems our timeline faced when supersonic travel suddenly made these effects non-negligible. The philosophical consequences of relativity deepened as the theory's implications permeated intellectual circles. The growing acceptance that measurements of space and time depended fundamentally on the observer's state of motion resonated powerfully with modernist movements in art, literature, and philosophy. The Cubist revolution in visual arts, emerging around 1910, found direct inspiration in relativity's challenge to absolute perspective. Writers like Marcel Proust and Virginia Woolf explored subjective experiences of time in ways that consciously echoed Einstein's physics. Philosophers of science grappled with the epistemological implications of a theory that made the observer's frame of reference central to physical reality itself. Educational systems worldwide completed their adaptation to the relativistic paradigm. By 1915, even secondary school textbooks presented relativity as fundamental physics, with Newtonian mechanics explicitly framed as a useful approximation for everyday speeds and gravitational fields. University physics departments had fully reorganized their curricula around space-time geometry and tensor calculus, producing graduates fluent in mathematical tools that wouldn't become standard in our timeline until after World War II. This created a generation of scientists equally comfortable with abstract theory and practical application, accelerating progress across multiple disciplines. The social impact of relativity became increasingly apparent as the theory's metaphors spread through popular culture. The concept that different observers could legitimately perceive different realities, while all being correct from their own perspectives, provided powerful analogies for cultural relativism and tolerance. Political movements advocating international cooperation found inspiration in relativity's demonstration of fundamental connections across seemingly separate reference frames. Even as these social applications sometimes stretched the scientific concepts beyond their intended meaning, they reflected how deeply Einstein's ideas had penetrated public consciousness. The most profound theoretical development of this period came with the first attempts to reconcile relativity with the emerging quantum theory. In our timeline, this synthesis wouldn't begin in earnest until the 1920s, but here, the process started earlier and followed a different path. With relativity already well established, physicists working on quantum phenomena from the outset framed their theories in relativistic terms. This head start would prove crucial in avoiding some of the conceptual difficulties that plagued quantum field theory in our history. By 1918, preliminary versions of what we would recognize as relativistic quantum mechanics were already taking shape in papers by European theorists. As World War I engulfed Europe, relativity's military applications became unexpectedly relevant. While the technology to weaponize mass energy equivalents remained decades away, relativistic corrections proved valuable for long-range artillery calculations and the synchronization of geographically dispersed forces. More importantly, the international nature of scientific collaboration on relativity provided one of the few remaining bridges between warring nations, as physicists on all sides recognized their shared commitment to truths that transcended national boundaries. Einstein himself now an elderly statesman of science, became a vocal advocate for using the universal language of physics to promote peace and understanding. By 1920, the world stood on the threshold of even more revolutionary developments. The foundations had been laid for technologies that would harness relativity in ways previously unimaginable, from precision global positioning to particle accelerators to eventual nuclear energy. More fundamentally, humanity's conceptual framework had shifted irreversibly. The notion of a fixed, absolute universe had given way to a dynamic, interactive cosmos where observer and observed were fundamentally linked. As the new century progressed, these insights would spread beyond physics to transform chemistry, biology, and ultimately our understanding of what it means to be human in a relativistic universe. As the world entered the third decade of the 20th century in this alternate timeline, the scientific landscape presented a fascinating paradox. Relativity theory, now over 100 years old in its original formulation, had become as fundamental to physics as Newton's laws had been in previous eras. Yet, simultaneously, the emerging field of quantum mechanics was revealing an entirely new layer of reality at microscopic scales. The period between 1920 and 1940 witnessed the extraordinary intellectual drama of these two revolutionary frameworks being woven together into a coherent whole, a synthesis that in our timeline took until the late 19th century to achieve. The early attempts at relativistic quantum theory that had emerged in the 1910s now blossomed into full-fledged quantum field theories. With relativity already deeply ingrained in physicists' thinking, the mathematical formulation of these theories proceeded along more elegant lines than in our history. The Dirac equation, describing relativistic quantum particles, was derived as early as 1925, not by a single brilliant mind working in isolation, but as the natural culmination of collaborative work by several European research groups. This equation's prediction of antimatter was confirmed experimentally by 1931, giving scientists their first glimpse of the astonishing symmetry between matter and antimatter that would later prove crucial for particle physics. The development of particle accelerators occurred earlier and along different lines in this timeline. Recognizing that relativistic effects became significant at high velocities, engineers designed the first cyclotrons from the outset to account for the increasing mass of accelerated particles. This foresight allowed them to achieve higher energies sooner than in our timeline, leading to the discovery of the muon in 1934 and strange particles by 1938. These discoveries, coming decades earlier than in our world, forced a rapid evolution of theoretical frameworks to accommodate the growing particle zoo. The standard model of particle physics began taking shape in outline by the late 1930s, though many details remained to be filled in. Astronomy entered a new golden age as relativistic astrophysics came into its own. The understanding that gravity could bend light led astronomers to predict and then discover gravitational lensing by galaxy clusters as early as 1928. This provided not just confirmation of general relativity, but a powerful new tool for studying the universe's large-scale structure. The concept of black holes, still speculative in our 1930s, was actively discussed and searched for in this timeline, with several candidate objects identified by their gravitational effects on surrounding matter. The expanding universe model, incorporating both relativistic cosmology and quantum fluctuations, became widely accepted by 1935, resolving debates about the nature of nebulae that had raged for decades. Technological applications of relativity multiplied during this period. The most dramatic came in 1927 with the development of the first atomic clocks accurate enough to measure gravitational time dilation at terrestrial scales. By comparing clocks at different elevations, one in a mountain observatory, another at sea level, physicists could directly observe time flowing at different rates in different gravitational potentials. This concrete demonstration of Einstein's theory captured public imagination worldwide and found immediate practical use in geodesy, allowing unprecedentedly precise measurements of Earth's shape and gravitational field. Navigation systems underwent revolutionary improvements by incorporating full relativistic corrections. The first inertial navigation systems, appearing in aircraft and ships by the mid-1930s, accounted for both velocity, time dilation, and gravitational effects from the outset. This foresight would prove crucial as vehicle speeds increased in subsequent decades. Similarly, early radio navigation systems like the British oboe system incorporated relativistic timing corrections that gave them accuracy far beyond what was achievable in our timelines World War II. The cultural impact of the quantum relativistic synthesis was profound. Modernist art movements like Surrealism found inspiration in the strange, counterintuitive behavior of quantum systems viewed through a relativistic lens. Writers such as Jorge Luis Borges crafted stories exploring the philosophical implications of quantum superposition and space-time curvature, creating a vibrant genre of scientific surrealism. Composers like Arnold Schoenberg and Anton Webern experimented with musical structures that mirrored the probabilistic nature of quantum mechanics while still maintaining the relativistic framework of spacetime relationships between musical events. Philosophy underwent its own revolution as thinkers grappled with the combined implications of relativity and quantum theory. The Copenhagen interpretation of quantum mechanics, when viewed through a relativistic framework, suggested a universe where observation literally created different realities for different observers. This radical subjectivity resonated with existentialist philosophers like Jean-Paul Sartre and Martin Heidegger, who saw in physics a validation of their ideas about the constructed nature of human experience. At the same time, the mathematical beauty of unified physical theories inspired neo-rationalist movements that sought to extend this conceptual clarity to other domains of thought. Educational systems continued evolving to keep pace with these developments. By 1930s, even introductory physics courses presented relativity and quantum mechanics as interconnected frameworks rather than separate theories. This holistic approach produced generations of students who intuitively understood concepts like wave-particle duality and space-time curvature in ways that wouldn't become common in our timeline until the late 20th century. The mathematics curriculum, similarly, emphasized tensor calculus and group theory from early undergraduate levels, creating a workforce mathematically prepared for the challenges of modern physics and engineering. The social and political ramifications of these scientific advances were complex. On one hand, the demonstration of fundamental interconnectedness through both relativity and quantum theory provided intellectual support for internationalist movements and the fledgling League of Nations. On the other, the growing understanding of mass energy equivalence raised alarms about potential weapons applications, leading to early attempts at international controls on nuclear research. Einstein, now revered as the grand old man of physics, became an increasingly vocal advocate for using scientific knowledge responsibly, a stance that earned him both admiration and controversy. As the 1930s drew to a close, the stage was set for even more dramatic developments. The theoretical understanding of nuclear processes had advanced to the point where controlled chain reactions seemed imminent, promising both unlimited energy and terrifying weapons. Rocketry pioneers were beginning to consider how relativity would affect navigation in space. And the first inklings of what would become information theory were emerging from studies of quantum measurement. The world stood on the brink of transformations that would make the relativistic revolution's first century seem merely preparation for the wonders to come. As we bring our journey through this alternate timeline to a close, we find ourselves standing at the edge of a world profoundly shaped by ideas that arrived a century ahead of their time. The early publication of Einstein's relativity theories did more than accelerate technological progress. It fundamentally altered the trajectory of human thought, weaving the principles of curved spacetime, time dilation, and mass-energy equivalents into the very fabric of civilization. By the dawn of the 21st century in this imagined world, relativity is no longer a revolutionary theory, but a universal language, a lens through which humanity views everything from the smallest quantum fluctuations to the largest cosmic structures. The long maturation of these ideas has allowed them to permeate not just physics, but philosophy, art, governance, and daily life in ways both subtle and profound. The technological fruits of this early relativity revolution are everywhere apparent. Global positioning systems, designed from their inception with relativistic corrections, guide travelers with uncanny precision. Nuclear power plants, their safety protocols refined over a century of peaceful development, provide abundant clean energy. Spacecraft navigate the solar system using propulsion systems that account for both general relativistic curvature and the time dilation effects of high velocities. And quantum computers, their architectures rooted in relativistic field theory, solve problems that would have been unimaginable just decades earlier. Yet the true legacy of this early relativity revolution lies not in devices or discoveries, but in how humanity conceives of itself within the cosmos. Generations raised with the understanding that space and time are fluid and interconnected have developed an instinctive grasp of cosmic perspective, a recognition that our planet is but a pale blue dot suspended in a vast, dynamic space-time continuum. This awareness has fostered both humility and ambition. Humility in the face of the universe's grandeur, and ambition to explore and understand it more deeply. The philosophical and cultural impacts are equally profound. The relativity of simultaneity has become a metaphor for cross-cultural understanding, reminding us that different observers, whether in motion or from different civilizations, can experience valid but distinct realities. The warping of space-time serves as a poetic analogy for how mass and energy, both physical and social, shape the trajectories of everything around them. These concepts have become part of humanity's shared intellectual heritage, referenced as readily in literature and art as in scientific papers. As we return from this thought experiment to our timeline, we're left with a poignant realization. The universe's truths exist independent of when we discover them. Whether revealed in 1805 or 1905, the fabric of space-time bends the same way. Light follows identical geodetics, and energy and mass remain interchangeable. The only difference is how long we have to live with these truths, to absorb their implications, and to let them shape our civilization. In our world, where relativity's revolutionary impact is barely a century old, we stand at what might be considered the adolescence of our relativistic understanding. The alternate timeline we've explored suggests the possibility of a more mature relationship with these ideas, one where their strangeness has faded into familiarity, where their implications have been fully digested, and where their potential has been methodically realized. Perhaps the greatest lesson is this: the most profound scientific truths, when given time to permeate a culture, can transform not just what we know, but how we think. As we continue to explore the implications of relativity in our own timeline, as we grapple with black holes, gravitational waves, and the possibility of warp drive, we do so standing on the shoulders of a giant whose ideas came to us precisely when they did. And yet, in imagining their earlier arrival, we've glimpsed a tantalizing vision of how deeply and beautifully human civilization can integrate profound cosmic truths when given sufficient time to let them unfold. So as we conclude this journey, let us carry forward not just the scientific insights, but the broader lesson that patience with ideas allows them to bloom fully. That time itself, whether flowing uniformly or at differing rates, is the medium in which understanding deepens, and that the universe will always have more wonders to reveal in their own perfect timing. As our journey through space-time comes to a gentle pause, we're left with a quiet realization. Einstein's revelations were never just about physics, but about learning to see the universe through wiser, more humble eyes. The equations may describe light and gravity, but their greater gift is the perspective they offer, that every observation depends on where and how we're moving, that time itself is fluid, and that even the most fundamental truths reveal new depths when examined from another frame of reference. Perhaps this is relativity's final lesson as we prepare for sleep, that rest, too, is relative. Your quiet night here on Earth is a different experience than someone orbiting above or a photon racing light years away. Yet in this infinite cosmic dance of perspectives, your moment of stillness matters just as profoundly. Thank you for letting these ideas bend your thoughts as gravity bends starlight. May your dreams find interesting reference frames of their own, where time stretches comfortably and the fabric of imagination warps in wonderful ways. And when you wake, remember, you're always simultaneously at rest and in motion, depending on who's observing. Good night from this particular coordinate in space-time. Sleep well, listener.